Hello and welcome to Math with Mrs. Becker. Today in calculus, we are going to start looking at some optimization problems. And what that means is we are looking for highest and lowest points, and we will definitely turn those into some application examples. One of the most important applications of the derivative concept is optimization problems. When you're looking at that, some quantity must be maximized or minimized. So here are some real-life examples. An airline must decide how many daily flights to schedule between two cities because they want to maximize the profits. Let's say you're a doctor. A doctor wants to find the minimum amount of a drug that will produce the desired response in his or her patients. So there you want to minimize. You don't want to give somebody more of a medication than what's needed. A manufacturer needs to determine how often to replace certain equipment to minimize maintenance. Okay, you don't want to be hiring somebody to come fix stuff. So you need to figure out how can you minimize that maintenance and replacement costs by knowing when to replace your equipment. Okay, so this is real life stuff and it's so fun. For each example, we will find or construct a function. Okay, the first two examples, they're going to give us a function. Then on the back side, we have to make our own function, okay, or a mathematical model for the problem. Then, by taking those skills that we did in 2.3 and 2.4, where we learned how to sketch the graph of a function, we can find our optimization because you guys were looking for maximums and minimums. And that's what we've been doing as we've been sketching. So you've done this process. We just haven't applied it to real life yet, okay? When you're finding your maximums or your minimums, the y-coordinate is the maximum or the minimum. The x-coordinate is just when that occurs, okay? So here's an example. We're using our curve sketching technique from 2.3 and 2.4. We want to find the minimum value, and we are looking for x values that are greater than or equal to 0. So that means if we end up with something that's negative, we get to just omit that. I have a function. So what I need to do, if I'm looking for maximums and minimums, you guys, you have to do the first derivative. The derivative of 2x cubed is 6x squared. The derivative of negative 15x squared is negative 30x. The derivative of 24x is 24. The derivative of 19 is 0. Now, in order to confirm if it's a maximum or a minimum, you need to understand concavity, which is the second derivative. The derivative of 6x squared is 12x. Minus the derivative of 30x is 30, and the derivative of 24 is 0. So the first step in trying to identify maximums and minimums, again, it's going to feel like deja vu. I'm just showing you that you do already know how to do this, okay? You take the first derivative and you set it equal to 0. 6x squared minus 30x plus 24 equals 0. Now make your life a whole lot easier. Everything here is divisible by 6. I would have x squared minus 5x plus 4 equals 0. Now, you guys, I can factor this. Two numbers that multiply to positive 4 but add to negative 5, well, that's negative 4 and negative 1. So when you set each group separately equal to 0, if I take x minus 4, set it equal to 0, I'd have to add 4. 0 plus 4 would give me 4. Now, if I took x minus 1 and I set it equal to 0, I would have to add 1. 0 plus 1 is 1. So the possible location for a minimum value is what we're looking for. These are the locations where you might have a maximum or a minimum. X would be 4 and 1. The way that you check to see if it's a maximum or a minimum, you fill it into the second derivative to check for concavity, because these are the locations on your graph where you have a slope that is equal to 0. Because remember, your first derivative indicates slope. So that's why we set it equal to 0, because if you have a maximum or a minimum, you do have a horizontal tangent line. It's all tied together. If I take the second derivative and I fill in a 4, 12 times 4 minus 30. Well, 12 times 4 is 48. 48 minus 30 is 18. This is positive, so this is concave up. So that means that we have a minimum value there. Second derivative, if I fill in a 1. 12 times 1 minus 30. 12 times 1 is 12. 12 minus 30 is negative 18. So when x is a 1, it's negative, so it's concave down, which makes that a maximum. Now the question says, find the minimum value. The minimum occurs when the x value is 4. They want you to find the minimum value, which is the y value at this location. In order to find the y value, what you have to do is plug it into the original. So 2 times 4 to the power of 3 minus 15 times 4 squared plus 24 times 4 plus 19 is 3. The minimum value is 3. It occurs 4 units to the right if we were graphing. Okay, now it says to use the curve sketching techniques. This is just relating it to our curve sketching sections 2.3 and 2.4, just reminding you that all of this is tied together. So the same as we had to do in 2.3 and 2.4, we started off by finding first and second derivative. To find your possible maximums and minimums, you still set your first derivative equal to 0. To see if it's concave up or concave down, you still use that second derivative. So again, you're kind of sketching so you can identify maximums and minimums. Your actual answer for this problem, though, would just be 3. That is your minimum value, okay? Let's look at a real-life problem. Suppose that a ball is thrown straight upward or straight up into the air, and its height after t seconds, okay, so t represents seconds, is 4 plus 48t minus 16t squared feet. Determine how long it will take for the ball to reach its maximum height. So we're trying to optimize. We want to know when the highest is going to be and then determine that maximum height. Now, if you are like me, this drives me absolute bonkers, okay? We have a quadratic function, but it is not in standard form. So the first thing I have to do just for my mental space is I need to rewrite this. So I have negative 16t squared plus 48t plus 4. Now I am optimizing, meaning I'm looking for maximums and minimums. That takes a first and a second derivative. 2 times negative 16 is negative 32. I reduce the variable by 1, so it's a t, plus the derivative of 48t is 48. The second derivative, the derivative of negative 32t is negative 32. The derivative of 48 is 0. So if I'm looking at possible maximums and minimums, first derivative set it equal to 0. Negative 32t plus 48 equals 0. If I minus the 48 over, negative 32t equals a negative 48. Divide both sides by negative 32. If I take negative 48 and I divide it by negative 32, t is 1.5. And remember, t is seconds. So what they're telling us is optimization, either the highest or the lowest point, is going to occur 1.5 seconds after the ball is thrown. Okay, so we want to make sure that it's a maximum. So I fill it into the second derivative. Second derivative, 1.5. Well, this is a negative 32. This is constant. This means that this thing is always concave down. So that means that this point is indeed a maximum. So we know that the maximum height occurs 1.5 seconds after the ball is thrown. To find the maximum height, you have to fill your 1.5 into the original function. So negative 16, t is 1.5 squared, plus 48, t is 1.5, plus 4. Your maximum height is 40, and it said that it's determined in feet. So your solution here, determine how long it will take for the ball to reach the maximum height. It takes 1.5 seconds. So that is one solution. Determine the maximum height. The maximum height is the height that the ball is at that 1.5 seconds, and in this case, it's 40 feet. Okay, so real life example. Time to step it up, my friends. All right, real life example. You want to plant a rectangular garden along one side of the house with a picket fence on the other 3 sides of the garden. find the dimensions of the largest garden that can be enclosed using 40 feet of fencing. Okay, so here's your scenario. You want a garden, but you're going to put it up against your house. Okay, so you only need 3 sides. You want it to be rectangular. Fencing, when you looked, you have 40 feet. Well, obviously, if you're going to take the time to make a garden, you want it to be the largest possible garden you can make. So let's go ahead and draw this out. Here is the garden, right? Let's say this is X. If it's a rectangle, opposite sides must be congruent. If I say this is Y, then this would be Y, okay? But we know that the house is on one side. So let's go ahead and let's say that this is the house, okay? Because we want to make this the largest possible. I'm going to put this is the house. So this is where you need your picket fence. It's going to be so pretty. I'm sure it's a little white picket fence. Christmas time, you can put some lights on it. Okay, awesome. So this is what we have, you guys. Okay, so this says, find the dimensions of the largest garden. So we want the area maximized. Okay, so area is what we want to maximize because we want a large garden. Area of a rectangle is length times width, so it's X times Y. Now we have a constraint. When we're talking about the outside, we only have 40 feet of fencing. So this fencing, we don't need to use the house, okay, because they told us that we will not need fencing there. It's going to be right up against the house. But I have 2 Ys plus 1 X, and I only have 40 feet. Whatever you are trying to maximize, this is the equation that I need. In order to fill the constraint in, we need to go ahead and use the substitution method that we studied back in Algebra 1, Algebra 2, and College Algebra. I need to take my constraint and put it into the problem, okay? So let's say I want to get X by itself. I can take this 2Y and minus it to the other side. So X equals negative 2Y plus 40. This is the constraint saying that I only have 40 feet of fencing. I need to put it into the area because the area is what I'm trying to maximize. So instead of X, I substitute negative 2Y plus 40, and I still have a Y. So all I did is I took the X from the area, that's what I'm trying to maximize, substituted in what X is really equal to, which is negative 2Y plus 40. Now to cancel the parentheses, we distribute. So the area is negative 2y squared plus 40y. I want to maximize this. So you guys, this is so cool. We want to maximize the area, but we had a constraint, so we had to put the constraint into what it is we're trying to maximize. This is our function. This is our f of x. So if I find my first derivative, and I'm kind of a dork, so I just put area, first derivative of the area, negative 4y plus 40. Okay, I just found the derivative. The second derivative is negative 4. So if I want to know, here it's y. If I want to know the dimensions for y that can help me to maximize, make the largest garden, I take the first derivative, negative 4y plus 40, set it equal to 0. Well, if I minus 40, negative 4y equals negative 40, divide by negative 4, negative 40 divided by 4, negative 4 is a positive 10, and this is feet because we're looking at 40 feet of fencing. So we have a possible maximum or minimum if y is at 10 feet. So we need to make sure that we're maximizing. So I go to the second derivative. If I take the second derivative and I fill in a 10, the second derivative was a constant, it's negative 4. So what that means is that any place it's concave down, which means any value that I found when I took the first derivative equal to 0 and I solved, those are the values where we're going to have maximums. And that's great because that's what we want. So we do have a maximum when y equals 4 feet. In order to figure out what x is, I go to the equation that says x equals negative 2 times y. Y is a 10 plus 40. So x equals negative 2 times 10 is negative 20 plus 40. Negative 20 plus 40 is 20 feet. So if I am going to go ahead and make the biggest possible garden I can using a rectangular shape, putting it up against the house, the sides, this would have to be 10 feet, this would have to be 10 feet, this would be 20 feet, Sorry, there we go. And this would be 20 feet. And you could do that keeping 40 feet because this is 10 plus 20 plus 10. So you would have your 40 feet of fencing. The largest area that you would have is 20 times 10. So the area would be 200 feet squared. But what the question said is find the dimensions. Your dimensions are 20 feet by 10 feet. But again, we were maximizing the area, so I thought it'd be cool to go ahead and see what that area would be. In case you're like, holy crap, what just happened? I got another one, don't you worry. This time we want to minimize the cost, okay? So the manager of a department store wants to build a 600 square foot rectangular enclosure, okay? So right now, I know we're looking at area. Area equals 600 feet squared, okay? It's rectangular, so area equals length times width, okay? So right now I'm just kind of putting some of that stuff together as I read through the problem. Okay, so the manager of a department store wants to build a 600 square foot rectangular enclosure on the store's parking lot to display some equipment. 3 sides of the enclosure will be built of redwood fencing, and that costs $14 per running foot. The 4th side is going to be built from cement blocks, because maybe that's right against the road or something. So the 4th wall, they're using cement blocks, and it's spendier. It's $28 per running foot. Find the dimensions of the enclosure that will minimize the total cost. So this time, they just want to do this as cheap as they possibly can. Okay, so again, rectangular area, okay? Let's say this is Y, so this is Y. Let's say that's X, so that's X, okay? We know that the area is 600 and area is X times Y. We want to minimize the cost though, so I need to figure out this cost function, okay? It tells me that 3 sides are going to be redwood fencing at $14 per running foot. So let's just say, okay, this is 14, this is 14, this is 14. Let's say this is the highway, so they need to go ahead and do cement blocks here, so that would be 28. Okay, the reason why I need to do this is because what we're trying to do is minimize the cost. So the most important thing here is that I have a cost function. So the cost is, I have 14x plus 14y plus 14x plus 28y. Obviously, I can go ahead and combine like terms. 14x plus 14x is 28x. 14y plus 28y is 42y. This is the cost. I have a limitation. The area has to be 600 feet squared. So I need to fill my limitation into the cost. The cost is what I'm trying to minimize. So this is the outside function. I need to put this into the function. So let's say I try to solve for y. So y would equal, if I divide both sides by x, 600 divided by x. So what I have to do is go to the cost function, and I replace y with 600 over x. So I have 28x, for some reason I almost wrote 200, 28x plus 42 times y, y is 600 over x. Now remember, when you are multiplying fractions, because that's what we ended up doing here, it's top times top, bottom times bottom. So the cost function is 28x. If I have 42 times 600, this is 25,200 over x. But if I'm going to find derivatives, I need to realize that this is 25,200 x to the negative first power. That's the cost function. So I took the cost, but I filled in the constraint. I need to keep the area at 600 feet. So I solved for a variable. Then I could use the substitution property from algebra. I went ahead, so I have my cost function with the fact that the area is constrained to 600 feet. This is the cost with that constraint. Now if I am trying to minimize, we need derivatives. So the first derivative, this is 28. This would be negative 25,200 x to the negative power of 2. Then if I want the second derivative, because I need to confirm that it's really a minimum, the derivative of 28 is 0. Negative times a negative is a positive. 25,200 times 2 is 50,400, x to the negative power of 3. So here are my derivatives. If I want to know where, this is kind of wild, guys, but we got this. If I want to know where I have possible maximums and minimums, you take your first derivative and you set it equal to 0. So if I have 28 minus 25,200 x to the negative power of 2, so that means it's x squared. What I want to do is I'm going to add this over here, and I'm going to form a proportion. Remember, a proportion means that you have two fractions with an equal sign in between them. So I took this negative 25,200 over x squared and I moved it to the side. This side was just a 28, so I went ahead and I have it over 1. Now I can cross multiply. 28x squared equals 25,200. Divide both sides by 28. If I have 25,200 and I divide it by 28, I have 900. In order to solve for x, you have to take the square root of each side. Now, typically, because I'm canceling a power of 2, you would have to include both a positive and a negative. But in this case, our value of x is a dimension. We want to know how many feet this is. Well, you can't have a negative amount of feet. So in this scenario, we do only include the positive because only the positive would make sense. So x is 30 feet. That is the possible location where we might have a maximum or a minimum. So if I go ahead and put it into the second derivative, the second derivative, if I put in a 30, the second derivative was 50,400 times x to the negative power of 3. I'm just filling this in. 50,400 times 30 to the power of negative 3. I have 1.86 repeating. Okay. Now the reason why this is important is because at this value, at the 30 that we filled in, this is where the slope is 0. This is a positive value. All we needed to know is if it's positive or negative. That's why I didn't worry about keeping it as a fraction. I just plugged it in because all I needed to know is this positive or is this negative? It's positive, so it's concave up. That confirms that this is a minimum. We have a minimum value when x is 30. It says find the dimensions, so we need to know both x and y. I know x is 30. Y is 600 divided by x. Well, x is 30. So if I take 600 and I divide it by 30, I get 20 feet. So that means that we have a minimum cost. If the y, this is 20 feet, this is 20 feet, this is 30 feet, this is 30 feet. If I want to minimize the cost of building materials, that's what I would need to do. So when I drew this, I didn't draw it very good. This would be the longer side. This would be the longer side. This would be shorter. This would be shorter. This would be $14. This would be $14. This would be $14. This would be the 28. And again, this is 20, this is 20, this is 30, this is 30. But what we needed to know, your solutions, in order to minimize the cost for that department store manager, when they build that rectangular enclosure, they need the dimensions to be 20 feet by 30 feet. If you take 20 by 30, the area is 600, which is what he needed. You guys, that is the beginning of 2.5. There are 8 questions in the book that I think are awesome, plus we also have a worksheet. I hope you guys had a great time today, and I'll talk to you soon.